Hey guys, welcome back to the channel. Today we are diving into Insertion Sort, a simple yet effective sorting algorithm that works just like how we sort playing cards by hand. Before we jump into the animation, let's quickly go through a short summary of how it works. Insertion Sort builds the sorted array one element at a time. It picks an element and inserts it into its correct position in the sorted portion. This algorithm works best on small or nearly sorted datasets. Its time complexity is O(n) square in the average and worst case, but just O(n) in the best case. It's an in-place and stable sorting algorithm, meaning it doesn't use extra space and maintains the order of equal elements. Overall, it's simple to implement, just like sorting a hand of playing cards. Now let's move on and watch how it actually works with a visual animation. Let's walk through how insertion sort works on this array. We start with the second element 1. We compare it with the first element 3. 3 is greater than 1? Yes, it is. So we move 3 to the right and put 1 to its place. Now sorted portion becomes 1 and 3. Next we take 4. 3 is greater than 4? No, it is not. So we skip. No changes are needed over here. Now we move on to next one, that is 2. 4 is greater than 2? Yes, it is. So we keep going left. 3 is greater than 2? Yes, it is. So we keep moving left. Finally, 1 is greater than 2? No, it is not. So we move 4 and 3 to the right and place 2 to its correct position. And this process continues for each remaining element in the array. We keep picking up the next element, comparing it with the sorted portion and shifting the larger elements to the right. Each step inserts the current element into its correct position. By the end, the entire array is sorted in place without using any extra space. It's simple and visual way to understand how sorting can be done step by step. Now that we have seen how the algorithm works, let's move on to the next screen and look at the actual code implementation for this. Here's the Python code for insertion sort. We start from the second element since the single element is already considered sorted. Current value holds the element we are trying to insert into the sorted portion. We use position to scan backwards through the sorted part of the array. While elements are greater than the current value, we shift them one position to the right. Once we find the correct spot, we place current value there. This process repeats for each element, growing the sorted portion step by step. It's simple, efficient for small datasets, and doesn't require extra memory. Up next, let's take a look at time complexity of this algorithm. Insertion sort has a best case time complexity of O(n) when the array is already sorted. In the average and worst cases, as we discussed, it performs O(n) square comparisons and shifts. You can see the average case growth visualized in the graph on the screen. So it's efficient for small or nearly sorted datasets, but not ideal for large unsorted lists. And that brings us to the end. Let's wrap up on the next screen. Thanks a lot for watching, guys. Hope you found this helpful. If you enjoyed this video, make sure to hit the like button and don't forget to subscribe. I'll see you in the next one. Until then, keep learning, keep coding. Thank you.